Hello, everybody. I'm Tapo from University of Washington. You can just call me Tapo. I'm a research associate, which is basically just a fancy name for a postdoc. First of all, I just want to thank the organizers for inviting me to be a part of this workshop on shared autonomy. So today I'm going to give a talk on our project on robot-assisted feeding, exploring autonomy with perceived errors. Before I start, here is a snapshot of our group at UW. So you can see my postdoc advisor Sid with our robot Herb in between. I have to say that this work would not be possible without close collaborations with multiple people in this picture. So to start with, I want to show you our autonomous robot assisted feeding system. So here you see the robot autonomously picking up a tool, which happens to be the fork in this case, and then uses multiple modalities, vision and haptics, to pick up food items and feed someone. So for example, here, the robot goes on top of the plate. It can identify different food items using the visual modality, and using both visual and haptics modality finds out what is the appropriate way to pick up a food item, and then tracks the face and figures out how to transfer the bite to the person so that it's easy for the person to take a bite. Now, the question is, why did we choose this application? Why assisted feeding? According to a survey, which is almost like a decade-old survey, like 2008, there are around 12.3 million people in the US alone that needed assistance with ADLs, or activities of daily living. And feeding is one of the core activities of daily living, right? Where you have to feed yourself multiple times in a day. I believe this number goes to around 140 million across the world. Now, I have visited various care living, like assisted care facilities, as well as homes. And I have to say that caregivers are playing an amazing role. But even after that, care recipients may still feel embarrassed, rushed, or socially challenged. And these are not some adjectives that I made up. These are actually like things that people, like the care recipients, told me about how they feel. And it's also understandable, right? Like, imagine yourself asking someone else to feed yourself every morsel of bite in your day-to-day life. There's a huge lack of control and independence, right? Turns out this activity is also one of the most time-consuming activities for caregivers, and so it may increase caregiver burden. So robots have the potential to help with these tasks, right? Now, then the first point was, okay, then why don't we have a robot have a person actually teleoperating a robot using any interface and help do this task? Now, if you look at general teleoperation interfaces, or people in assistive scenarios, especially, for example, joysticks on wheelchair, or different interfaces that they use, like a sip and puff or head buttons and things like that, they're very low degree of freedom interfaces. So to perform an intricate manipulation task, such as feeding, it may require a lot of time. In fact, one of the JACO robot users that we interacted with, who had C1 quadriplegia, which means like basically spinal cord injury, C1 spinal cord injury, he had a very high mobility limitation, right? And he self-reported that using a completely teleoperated robot, it would take him almost 45 minutes to feed him just 3 pieces of solid food items, not even this particular chipotle ball, which is much more complicated than what he was referring to, right? And so it seems that for an intricate manipulation task such as this, autonomy is essential. But then we thought, okay, so if we need a robotic system to be autonomous, how difficult can it really be if we just want to pick up certain solid food items? So our first attempt, we actually developed a system where basically we just had a fixed control policy where the robot would go, we will attach a fork on the robot arm, and then the robot would go down and pick up a food item at a fixed depth. And turns out that even a simple strategy like this works pretty well for some food items, right? Simplicity rules. But when we try to increase the range of other food items, right, that's where it fails. And that is because like robot assisted feeding is very challenging. It's a hard problem because it involves bite acquisition, where you have to perceive the food in a cluttered plate and also manipulate these food items. And these food items are actually deformable objects of various physical characteristics. Like some food items can be hard, some can be soft. And so it's very challenging. Some can be slippery as well. In addition, the problem doesn't end there. Once you pick up the food item, the robot needs to be able to transfer the food item to a person's mouth. And that requires robot mouth handover. And the robot needs to figure out how to make it so that it's easy for the person to take a bite, right? So then our question was, okay, then given this problem is complicated, how do you even go about developing a robotic system that can do all of these things? So that's when we realized that, okay, we as humans, we are experts in feeding ourselves, right? Like we are eating every day, multiple times a day, using different tools like a fork or something like that. Why don't we look at ourselves? And so we did a study where we gave people probably the most expensive fork that they would ever eat food with. We gave a fork, we instrumented this with 4 stock sensors, motion capture markers. We attached other sensors around, and we asked them to pick up different food items of like different consistencies, and then feed a mannequin as if they would actually feed a person. And we found that inherently this process was multimodal. They saw and they felt what they were trying to do, and they were doing it, and based on the surveys that we did. Interestingly, we found some very fascinating trajectories that people use. For example, if you see this particular snippet, you see that the person, once they try to pick up the banana just slips off, right? Its texture is slippery. But then the person unconsciously, subconsciously, like tilts the fork so that the food stays on the fork. And the reason why it happens is it's basically physics, right? Once you tilt the fork, the gravity vector adds another frictional component that helps the banana to be on the fork. So it's just these simple strategies that helps you pick up these different things that we use all the time. So based on this, we developed a food manipulation taxonomy, where we found out different strategies. Like we classified these strategies into different discrete actions for acquisition as well as transfer. But these are different motions, and this is not the end of the story. We also found that people use different forces for dealing with different, like to skewer different food items. In fact, the forces were so different that using a temporal convolution network and just the z direction force, just with like less than a second, like around 0.7 seconds on average after skewering the food item, just with that data itself, using the force data, we could classify the food items into these different categories: soft items, hard items, or even items which have hard skin but soft inside. So you can see that participants use many very different forces. So based on this experiment, this gave us an insight into why our initial robot experiment failed. And that was because we are using a fixed position control policy. And what we actually needed is different control policies depending on the type of food items. And by control policies, I mean different motions and forces depending on the type of food items. So now that we know this, we thought, okay, we have some insight about this. Why don't we go and build a robotic system? So for that, the first step was to choose a hardware. And so we decided to go with the Jayco Kinova arm, mainly because first, it's like we can mount this on a wheelchair. It is actually used by people in their homes for assistive tasks, albeit complete teleoperation, but it is being used. And people can perceive this as an extension of their own arm. Also, we put everything on board, sensors and the compute on board. So for example, the computer is on the back of the wheelchair and thing. And so the idea is that a person can move with this like wherever and to wherever they go. So they could literally use this robot to feed themselves food item on one table versus another, or even at a different place. Now, in terms of adding sensors to it, we added, basically we developed this, the black box that you see here. It's a wireless perception module that we developed in our lab. And the reason we developed this was this, we use this to interface the vision sensor as well as a tactile, gel-based tactile sensor that we built for the Kinova arm inspired from the finger vision sensor. Uh, and the reason we built this was so to reduce the wiring. So the wires were very short, and so they would interface with this wireless perception module, and then the data would be transmitted wirelessly. And you may think this may be a trivial problem, but imagine someone, imagine a robot feeding someone a complete meal with all these different food items with intricate manipulation strategies. A wiring like this can get entangled and the feeding becomes infeasible after a certain point of time. So once we had these hardware components ready, we also built some system components where basically we use the vision part not only to detect food and face, but also for visual servoing. So even if the person moved during feeding, the robot would be able to track the mouth and feed, go near the mouth for feeding the person. We use the tactile sensor to be able to control how much force to apply. And this tactile sensor was sensing shear force. And so like how much force to apply to actually skewer a food item, and also for safety purposes. So to make sure that the robot is not poking someone. So now that we have all the system components ready, the next question was, how do you actually pick up a food item? So the first step is, of course, you need to be able to detect where that food item is. And then once you know that food item, where that is, how do you pick it up? Like what is the pose of skewering and things like that, right? To formalize this problem, basically, it boils down to selecting a control policy that maximizes the success rate given a target and an action. A target could be, like given an image of a plate, it could be any one food item at one particular bite. And the actions could be any of those actions that we found out from those taxonomy. And that's where that study feeds back in this, where the actions could be what actions to choose to not only pick up the food item, but also how to transfer the food item, right? Now, one thing to note here is that we had an insight, which is we cannot treat the problem of bite acquisition and bite transfer independently, because how you acquire the food affects how you transfer the food at a later stage. So you need to think about this beforehand to make sure that you pick up the food in such a way that eventually it becomes easier for the person to take a bite. So once this control policy is selected, we implement this basically as a mapping from image and haptic data to a delta position in the fork time. Now, so the way we implemented this was using basically like two networks. First, we had a RetinaNet that we fine-tuned on food data sets that we collected from real-world food data, as well as like basically 3D scan food data, where we developed an Unreal Engine plugin for OpenCV. And so this RetinaNet outputs bounding boxes around each of these food items. Now, once these bounding boxes are identified, they go as an input to this network that we developed in our lab, which we call skewering position action network. And the output of this network is basically the probability of each of the actions in its action space, probability of success where each of these for each of the actions in the action space, as well as where in the food item the skewering should be done. Now note that a skewering position action network, this SPANET, doesn't just take into account the bounding box of the food item, but it also takes into account the surrounding environment of the food item, because the strategy, the most successful strategy of picking up a food item depends not only on the food item itself and its characteristics, but also its surroundings. And we input this information as a one-hot encoding vector just before the final layer. So this is, to go a little bit deeper, this is how the structure of the SPANET architecture, where the input is the bounding box from the RetinaNet, and then we have a bunch of convolutional networks in near layers, a bunch of convolutional networks, and then at the end, just before the final layer, we add an environment classifier, which is added as a one-hot encoding vector. Now, output is a 10 cross 1 vector, where 6 elements are basically predicted success rates for our 6 actions in the action space, and the four elements are two endpoints of the main axis. So then we draw a line along this axis, and then the robot skewers at the middle of this particular axis. So now that here you see a performance where the robot goes and picks up different food items. And encouragingly enough, SPANET was able to generalize to unseen food items, where, for example, here you see instead of bounding box saying which is strawberry, which is bell pepper or carrot, it just says which is a food. And the robot can pick up the food item, whether it is in a cluttered environment like stacked on top of a lettuce or on an empty plate. Now, when we analyzed a little bit, we found that the way it was generalizing to some of these unseen food items was it was using characteristics such as shape, size, or color to be able to generalize. So for example, if it knew how to pick up carrot, it would know how to pick up a celery. Or if it knew how to pick up a spinach, it would know how to pick up a kale or a lettuce leaf. However, like there are so many food items in this world, right? Like it's so diverse, it's almost impossible to generalize from beforehand to all of these food items, right? At this point. Also, like it's very difficult to come up with a simulator that can simulate these food items where we can keep on trying out different actions, because it's just very difficult to model these kind of food interactions. So our obvious choice was like, can we leverage online learning, where the idea is that we observe the state. It can be anything, it can be an image or whatever. And then we choose an action from our action space. And then we observe the reward. And the reward could be, is the food on the fork or not? Like was the robot able to successfully pick up the food or not? And based on this, you can update the policy and we can go on, right? So for our particular system, this is how it would look, where basically the context could be an image in this case. And the policy could be our SPANET, which I talked about before, where the featureizer basically takes in this, and we take that final layer, where from there we sample a particular action, one of those actions, like from those 6 actions. So one of those actions in this case could be the vertical skewering. And then we actually execute this action, and we see whether the food item is on the fork or not. So it's like a binary reward, so success or failure, and based on this, we keep doing this. And the idea is to minimize cumulative regret, where say you have the context xt, and if you see the equation below, context xt, then you have a featureizer that converts it into a particular feature that we care about. And then the policy takes that feature and then returns, like basically takes a particular action, which could be any of the sampled actions. And then the CT is the cost, which tells the cost of this particular action. And we sum it over from the onset till our current point in time. And then we compare this with the best policy in class, and that's where we want to, and that's how we want to minimize basically the cumulative regret. And now to actually do this, there are many algorithms that are there. We tried out 2 options. One is a very widely known epsilon greedy approach, where the idea is that we choose to explore a random action with probability epsilon, but with 1 epsilon probability, we always choose the usual action that the best action that we have, we chose. Even though it's a very simple thing, empirically it turns out to be very competitive. We also, because of the nature of our map, where we have a linear function between cost and our the feature, the linear layer that we chose after the featureizer converted it, we also chose a lin UCB as one of our approaches, where the idea is to explore actions with higher variance. And so the insight is that there is a more chance, like there's a chance for improved regret, but it would sacrifice learning speed. Now, this is how the entire system would look like, where the top part you are familiar with, where you have, it's the same thing, where we had a RetinaNet, and then we had SPANET that takes into these bounding boxes. But then we have this linear map, and then we sample any of these actions, and then there is a feedback loop where we observe the reward, and based on this is repeated, right? So we implemented this on our robot, and here is a video which shows where you see the right action, right? Like the TA, the tilted action, is the correct action to pick up a slippery banana slice. Initially, when it started, it had low confidence in it. But with more and more exploration through online learning, it figured out, its confidence increased, and figured out how to pick it up. But even though it figured out how to pick it up, it does not forget how to pick up other food items before. that it knew how to pick up. And next time it says a ripe slice of banana, it can immediately converge to the right action. So by sacrificing one slice of banana, it could figure out how to pick up a banana from next time. However, like even though these are encouraging things, there is always, when we talk about all of these experiments that we did was in the lab, like specifically in the lab without our target population and like on the tabletop. But autonomous assistance in the real world is challenging because these errors are like, there could be errors and these are inevitable. The errors could be because of different preferences, like environment conditions may change. There can be uncertain environments, unstructured environments. So there could be various things, right? So what we wanted to do was we wanted to evaluate what we had so far. And so we thought we would evaluate it with our target population to close the loop. And we would try out we would try to simulate realistic scenarios that may occur in the real world. And so for that, we looked at various user preferences, but for this purpose of this talk, I'm just going to focus on levels of autonomy. We also, where we basically looked at different levels of autonomy, and we found out what we wanted to know, what our target population actually prefer, because our entire premise started with that we need we need autonomy, but do people actually prefer it, right? We also, and so here is how our like experimental setup looked like, where obviously we had the full autonomy version on the left, as you can see here, where the only interaction that happens is that user selects the food item through an interface. It could be anything. So for example, if the user were to use voice interface, it would say, like we had actually connected Alexa with this, but we can use any voice assistant. So for our particular system, the user would sit in the wheelchair and say, "Hey Alexa, tell the robot to pick up a strawberry," or "Hey Alexa, tell the robot to pick up a watermelon," or something like that. And after that, the robot takes care of how to acquire the bite, how to transfer the bite, and when to feed the bite, everything autonomously based on its own algorithms that I covered before, right? So it's full. This is what we call full version. Now in the low autonomy version, what we did was, again, as I said before, for this intricate manipulation task, complete teleoperation was infeasible. It would take so much time that people won't be able to even feed themselves a complete meal. So even for a low autonomy version, there was a significant amount of intelligence already there in the robot. But what changed was, in addition to the user selecting food item, user for each of these phases, like how to acquire bite, how to transfer the bite, like what action to choose to transfer the bite, and when to feed a person, this was all told by the user. So the user would say how to transfer the bite so that it's easy for the person to take a bite, how to pick up the food item so that the robot would be successful, or when to feed the person. And the partial autonomy version was a version where we basically just one of these three phases out of these three: acquisition, transfer, and timing phases, one of these phases was autonomous and everything else was non-autonomous. So we experimented with all of these versions. So for example, here is a trial where you see a person with mobility limitation. He's using head button. So every time you see he's tilting his head and using a web interface to select the option. And every time he tells the robot what to do, and then the robot does the thing. So he chooses an action to pick up a food item, how to transfer the food item, and then when to bring the food item, and then the robot brings up the food item. So we did that experiment. Now, coming back to the original point, we also wanted to see, okay, for the more autonomous versions, there could be errors, right? So we wanted to simulate this by deliberately introducing errors in the acquisition, timing, and transfer phases. So for example, in the acquisition phase here, the robot deliberately fails to pick up the strawberry in this case. And so here you see the robot will fail pick up, and you can see the reaction on the user's face, right? We also added a timing error where the person opens the mouth to tell the robot to come, but the robot is late. So there's a timing error, and the person is is expecting what's the robot doing, right? The second and the third one is a transfer error where the robot deliberately misses where the face is, goes somewhere else, and then and then goes back, right? So the way we did this experiment was we intentionally introduced these errors, of course, randomly, but the way we introduced these errors is after the error, the robot corrected itself after one try, right? And then we asked people that if these errors are inevitable when the environment becomes even more unstructured and uncertain in the real world, and robot may not even correct itself after one try. So if these errors happen, would you be even willing to use this robot, or how open would you be to, like, to use this? What levels of autonomy would you prefer? And the results that we found were very interesting. First, in terms of autonomy, almost every participant agreed that the low and the partial autonomy versions required more effort than full autonomy. However, they did not find any significant difference between, we could not find any significant difference between low and partial autonomy. And that is probably because even our low autonomy has some intelligence in it. It is not complete teleoperation, right? However, when we analyzed the presence of errors and no errors, we found something very interesting. We found that people with high mobility limitations, right? For example, people with C1, C2 spinal cord injury with very limited movement, they preferred more autonomy even with perceived errors, because they liked a system with as little intervention required as possible, even if the errors happened many times. In fact, some of the participants said that even if the robot failed to pick up a food item once in every 2 or 3 trials, they would be totally fine with using full autonomy instead of telling the robot every time what to do. However, people with low mobility limitations, like people with C5, C6 spinal cord injury, who had more movements, right? They could move their arm, but they could not probably feed themselves for a long time. They had high expectations from the robot. So they said, if the robot fails to pick up a food item or has these errors more than 10% of the time or 20% of the time, they would not want to use this robot in their real life. So what that means is there is no universal design or universal answer. And it's not just based on user preferences, but it's also based on the user's condition itself, specifically in the assistive domain. However, regardless of their mobility limitations or their preferences, everybody was very accepting of this system. As you can see from one of the comments here, the technology allows me to do more things on my own, of course, giving me more independence, making me feel more free, and gives me something to look forward to. So it's comments like this that continues to motivate us to keep on working on this problem. Here is a small video snippet where you see people with different interfaces. Some people are using sip and puff. Some people are using their arms where they could move a little bit, right? Some people are using head buttons. Different people are using different interfaces to feed themselves different, like these food items. So the key takeaway from this talk is that assistive feeding is a very interesting domain because it's a high impact task, but at the same time, very technically challenging task. However, we need to be careful about designing a stiff system because every system can benefit from flexibility in the system. And what I mean by that is if we care about assistive technologies helping people in the real world, we need to give these systems multiple options of different levels of autonomy, as well as different other options so that it can adapt not only to user preferences, but also users' physical condition itself. Another thing that we as engineers sometimes tend to forget is that we always strive for, like maybe it is not even needed to have perfect accuracy in the system. Because if we want to wait to have a perfect accurate system, perfect performing system, when can we actually deploy this? Is that even possible? So turns out that depending on the user base or our target population, maybe 75% accuracy is enough to be able to deploy this in the real world and try out and see what happens, right? So to design any kind of robotic system that helps people and that interacts with people in the real world, maybe the target performance metrics should come from the user themselves. And it is always not necessary to come up with a perfect performing system. So So based on this, we are working more on coming up with a system that we hope to test out for long term with this target population in their homes in future. Here are some open data sets that you can try out. The human data of trajectories, as well as data set of mood manipulation strategies and different food images. So feel free to try out your algorithms and everything with these data sets. And this is basically, this is how I would like to conclude my talk. One thing I wanted to add at the end is that so I'll be joining Cornell Computer Science as an assistant professor in future, and I'm looking for students and postdocs. So if you are interested in working with me and working in these kind of things like manipulation, human-robot interaction with focus on assistive technologies, please feel free to email me. Like you can find my email like tapo@cs.washington.edu. And I know this is a video, but I would be happy to answer questions because I'll be available. Please post your questions in the workshop Slack channel, and I would be happy to answer those questions when I come online. I'm sorry I could not do this live because of these time differences, but I'll be happy to answer these questions when I come online in the Slack channel. Thank you so much.